Welcome back to Chem 4300. In this video, we're going to begin Chapter 10 on wave-particle duality. Now, in the material leading up to this chapter, we've been looking at how to apply classical physics to describe the motion of atoms and molecules. And so we were using the same Newtonian physics that you would use to describe the motion of billiard balls on a pool table, or a rocket flying through space, or a planet orbiting a sun, to describe the translation and rotation and vibrational motion of atoms and molecules. Now, it turned out that actually worked out pretty well. For example, in the case of the kinetic theory of gases, we were able to get a pretty good understanding of the distribution of speeds and energies and understand concepts of temperature. And when we went into the chapter on equal partition of energy theorem, we were starting to get a pretty good idea of how to understand heat capacities in terms of that motion. But it was in that chapter that we noticed something was a little off, particularly when we looked at diatomic molecules or polyatomic molecules. We saw that for some reason we weren't getting the vibrational energy contribution to the heat capacity. And at the time, this bothered a lot of people looking at trying to understand the microscopic nature and the motion and how it relates to macroscopic properties. But no one was questioning the use of the classical physics at the time. So, there was a quote from even around 1900, Lord Kelvin, who said, "There's nothing new to be discovered in physics now. All that remains is more and more precise measurements." And what we're going to learn in this chapter is that, in fact, actually this is wrong. There was actually new physics that was about to be discovered, and it was related to some of those little discrepancies, those weird things regarding heat capacity and other types of experimental results. So what we're going to do is we're going to look at some of these other experimental results and see how they led to some new insights on how to understand what's happening at the microscopic level. So the question we're going to start out with is this question: why do objects glow when they get hot? And back in the 1800s, this was actually an important scientific question, because that was the time when light bulbs were starting to be introduced into everyone's home, and they never had to use candles again to light the home. And there was a lot of effort to try to understand how to make better light bulbs. And so they knew that if they passed electricity through a filament, they would heat the filament, and the filament would glow with this kind of behavior. As it got hotter, it would glow brighter and at actually higher frequencies. So what we know actually is that if you heat an object, that it will start to glow. First it will be kind of red, then it will kind of go orange, turn to yellow, and finally a bluish white, and at the same time increasing in intensity as you keep increasing the temperature. And we know, and at the time they also knew, that heating an object increases the microscopic motion of all of its molecular constituents, right? So all of the components, the atoms and molecules, would start moving faster and faster as you heat the objects up. And all of those guys, the atoms and molecules, had some kind of electric monopoles, dipoles, or other kinds of multipoles associated with them. And that motion was going to generate electromagnetic waves. So all of this kind of motion, the dipoles tumbling, vibrating dipoles, or other types of motion, should be generating light, and there should be more light as you increase the motion, which increases with temperature. So that all made good qualitative sense. So it was expected that objects would glow as they became hot. But the details then started to be a little bit confusing. So one way we can look at an object glowing is to look at the light intensity as a function of frequency or wavelength. This is something called the spectrum of the light emitted. So the light intensity or density as a function of frequency or wavelength is something that is called the spectrum of an object. And that will depend on the object's composition, but generally speaking, there are a class of objects that we call black bodies that have the same thermal spectrum. So all objects, when you heat them, will glow. And the general form of that spectrum behaves the same for all objects. Now, there'll be some weird little differences depending on the composition, but the general sort of shape of that spectrum as you change temperature will be the same, and that general shape is what we call the spectrum of a black body. And the reason we use the word black body is because a black body is non-reflective, so it absorbs all the light that's incident upon them, and they appear completely black. And if you were wanting to study the light that's given off by an object, then you would want to make sure that the light that's coming off is generated by the hot object and not light that's being reflected off of that object. So any reflectivity of the object would be a bad thing, because then you would be measuring some other light source as opposed to the light that's being generated by that hot object alone. And so a black body is something that absorbs all light and reflects nothing. So that makes it the ideal sample if you want to study the thermal spectrum of that object, the energy that the light is given off as a function of temperature. So a couple of things that's sort of useful in this definition is the light absorptivity of an object, alpha, is the fraction of the incident light power absorbed by a real body when it's emitting or absorbing at some temperature, when it's in thermodynamic equilibrium. And the light emissivity is the ratio of the emissive light power of any real body to the power of an otherwise identical black body. So real bodies will reflect a little bit and have some deviations, and so that's the difference between these guys. This ratio is what's called the light emissivity, and that, generally speaking, these are going to depend on wavelength. Kirchhoff's law tells us that at equilibrium, the absorptivity and emissivity are equal to each other. Now, a perfect black body will have these guys equal, the absorptivity and emissivity equal to 1 at all wavelengths. So that's what we mean by a perfect black body. So it's the ideal case. And of course, when you get a black body hot enough, then they'll eventually start giving off visible light and they become self-luminous. So real bodies then, are going to be a little less than these values. Engineers often make this something called a gray body approximation, that you have some value that's less than 1, but it's independent of wavelength. But most non-metallic surfaces, we're going to find that this value is pretty close to 1. Here are some typical values. If you just take charcoal, for example, which is, is very black, that has an emissivity close to 1, so it's a pretty good black body. You can buy special paint from 3M that actually gives you perfect behavior in terms of the emissivity. Other types of non-metallic materials will give you pretty good black body behavior, but if you have any kind of polished surface where you have lots of reflectivity, then you see you have very low emissivity, and those aren't going to work very well as a black body. Now, if we go back to that spectrum, so this is the spectral radiance of a black body, and this is as a function of frequency here. And you can see the behavior that we've been talking about so far, that the most intense light frequency shifts to higher frequencies as you increase the temperature. So you can see here's 1,000 Kelvin, 1,500 Kelvin, and 2,000 Kelvin, and you see the peak shifts to higher frequency as we increase the temperature. We also see that the area under the curve increases with increasing temperature. So you see the area here at 1,000, 1,500, 2,000 keeps getting higher and higher. The radiant emittance, which is this quantity J, comes from the area that's underneath the curve, and that's given by this expression. This is the power emitted per unit area of the black body surface. So trying to understand the shape of this curve and its behavior with temperature was something that was on the minds of a lot of scientists in the late 1800s. Now, experimentally, it was found that this emittance is proportional to the temperature to the 4th power, so that whatever the temperature of the object is, raise it to the 4th power, and then there's one constant for perfect black bodies, which is called the Stefan-Boltzmann constant, that tells you how much light is going to be given off. So this was a very important relationship. And of course, if you have emissivities that are slightly less than 1, then you sort of just modify this, but it's still going to be proportional to the temperature to the 4th power. So that was an important experimental result that was found by looking at black body spectra. Additionally, another important result was something called the Wien displacement law. This was experimentally found, and this was pointing out how the wavelengths shift with increasing temperature. It turns out that if you look at the maximum wavelength, so the wavelength where the intensity is maximum, so I'll call that lambda max, if you multiply that times the temperature, it's always equal to a constant regardless of the temperature. So as the temperature increases, the wavelength will decrease in such a way that they maintain a constant value, which is called the Wien displacement constant. And this is actually responsible for a number of important properties of glowing objects. And so one of the things that, from terms of the light bulb story, is that the temperature of the light bulb comes from Wien displacement law. So we know that if you look at the light bulb and you look at where the light intensity has the maximum intensity, the wavelength that has the maximum intensity, then the light bulb's temperature is just given by dividing that wavelength into the Wien displacement constant to get the light bulb temperature. So when you go to the store and you buy an LED light bulb, one of the things that you'll see on the bulb is a temperature telling you through the Wien displacement law where the light intensity has the maximum intensity, what wavelength has the maximum intensity. So it's a little strange. You would think that if you go by the bulb, you might just see this light bulb has maximum intensity at this wavelength, and they just give you the wavelength, but they don't do that. They give you the temperature of the bulb through this Wien displacement law. So I'm not sure why. But what's interesting is that if you have an old-fashioned or incandescent bulb and you dim it, and you turn the little light dimmer down, you'll find that the temperature or the wavelength will get to longer and longer wavelengths or lower frequencies as you dim the light. So as the light dims, the temperature changes. So the temperature of the light bulb when the light is very bright is a high temperature, and when the light is very dim, it's a low temperature. And one of the things that's different with the LED bulbs versus the incandescent bulbs is when you dim the LED bulbs, they generally don't change their wavelength. The wavelength of maximum intensity stays constant as you dim them, whereas an incandescent bulb would actually move down to longer wavelengths or lower frequencies as you dim them. Now, another application of Wien displacement laws is in the field of optical pyrometry. So if you have a glowing object, you can just measure the light spectrum and find the max, and you can figure out what the temperature of the object is. So the one obvious example is if you look at the sun, you find that the sun has maximum output of light at a frequency or a wavelength of 510 nanometers. From the Wien displacement law, we see that that associated with 5682 Kelvin. That's the temperature of the surface of the sun. Similarly, if you looked at another star, say the North Star, you'll find that its light amplitude is maximum at 350 nanometers. And so that corresponds to a much hotter star, which has a surface temperature 8279. Now, getting the spectrum of the sun was first done in 1817 by Fraunhofer. He actually developed the spectroscope that was able to measure the sun's spectrum and measure the intensity of light at each of the different wavelengths. And this is what he measured. This is actually commemorated in a 1987 stamp in Germany. But it also shows us another interesting feature that he saw in the sun spectrum. So you see the black body radiation curve. This is a function of wavelength instead of frequency, so it looks a little different than the previous slide. But this is the classic black body radiation curve. But he also noticed that there were some dark lines in it, some regions where the intensity would drop down really sharply as he moved across at wavelengths here in acquiring this spectrum. And he realized, as he looked at the positions, the wavelengths of all these dark lines, that they were similar. Some of them were similar to where the lines that you find in a salted sodium flame. So in other words, if you take remember that experiment you do in high school chemistry or freshman chemistry where you take a wire and you dip it in a sodium chloride solution and you put it into the flame and you see it glows with a very bright yellow color, and then you take, say, potassium salt and you put it in, you get different purplish color. So these colors that you get when you put the salted wire into a flame were measured also with the spectroscope, and they were found to be very sharp lines, and the positions of those lines were agreeing with some of the dark lines in the spectrum. And in fact, actually, other people who recognized this went and looked at other types of lines of atomic elements and found that they could assign many of the dark lines to wavelengths associated with what they would find in these salted flames with these assignments here. So what this was telling them was that the sun was composed of these elements, and the light that was being emanated from the sun was being absorbed by these elements. So in the flame they were emitting, but in the sun they were absorbing. They were absorbing light at these wavelengths, and so the light that reached Earth was lacking some of these wavelengths because they had been absorbed before they were able to escape from the sun and get to the Earth. So all these lines here were very important in telling us the composition of the sun, in addition to sort of having this overall shape was the black body radiation. Okay, so now what we're going to do is we're going to go and look at the first serious attempt to try to model that curve. So we want to find a way to model, I'll just put it here, this curve for on the basis of all the physics that we know up to this point. And one idealization of what could be a black body was a small hole in the cavity of some metallic box. So in other words, if you have a box that has imagine some 3D box, and you have just a tiny hole in that box, that hole is an ideal black body. And the reason it is because we know that an ideal black body absorbs all light and emits nothing, right? So all the light shines onto a black body, gets absorbed. So all the light that hits this hole will get absorbed. And the reason it happens is, imagine some light beam coming in. If it comes into the hole, it will hit the wall, and some of it will be absorbed by the atoms and molecules in the wall, and then it will bounce off and it will hit another part of the wall where, again, some will be absorbed, and then continue to bounce around inside this box, and eventually it will be completely absorbed, and none of it will be able to manage to reflect and come back out. Now, if we're talking about a big box and a very tiny hole, then the chance of light going in, finally working its way out, is going to be pretty slim. So that hole acts like an ideal black body. So this was sort of picked as one example that we could use to try to model what is a black body. And similarly, if you have this box at some temperature, some finite temperature, then the atoms and molecules in the wall will be moving and radiating, and they will be pushing light, electromagnetic waves, into this box. And then if you were looking at what was coming out of this hole because of the finite temperature of this box, then you should get a black body spectrum. All right. So what Raleigh and Jeans did was they tried to take that model of a black body and see if they can derive an expression for the black body spectrum. So they said, let's assume that the walls are metallic. So that means that if the box is grounded, the electric field has to go to 0 at the walls. And then they said, okay, now we have a whole bunch of electromagnetic waves that have been pushed into the box from the molecules that are moving in the walls of the box. And if you remember, we learned how to calculate the normal modes that are in a 3D box. And one of the things that we learned was that there are degeneracies in wavelengths or degeneracies in frequencies, right? In 1D, there were no degeneracies, but in 2Ds, we started to see that there were multiple normal modes that led to the same frequency. In 3D, there were even more normal modes that would lead to the same frequency, and these increased as you went to higher values of n, or nx, ny, and nz. You had greater ways of doing that, and we worked through some examples. So what they asked was, how many normal modes are going to be in a frequency interval between, say, nu and nu plus d nu? And they worked out, and this is something that you could do too, they worked out that the number of normal modes in this interval was going to be given by 8 pi, v is the volume of the box, divided by c naught to the third power, that's the wave speed, which is the speed of light, times the frequency squared, and then d, so nu squared d nu. So this was the number of modes, the density of the number of modes, the probability density, except this is not a probability, actually this is a number, which is the number of nodes, but it's a continuous function when we get to this large value of n values, so nx, ny, and then z in our 3D box. So this is the expression they found. That's something that's correct. We know that's correct. You would have been able to derive that before. Now, to predict the black body radiation spectrum, they needed to figure out how much energy was associated with each normal mode in the box. So for each normal mode, for a specific nx, ny, and nz, there was some energy associated with that standing wave pattern. And of course, we know from classical electromagnetic theory that the energy of the wave is proportional to the amplitude of the wave. The bigger the amplitude of the wave, the more energy it has. The smaller the amplitude, the less energy it has. And so they took this equal partition of energy approach. They said that the energy that was coming from going into the box was going to distribute itself over all possible normal modes, right? Because the energy, all the normal modes had some energy that was proportional to amplitude. So whatever energy was being put into the box by the molecules that were vibrating and putting light into the box, that energy had to distribute over all the normal modes. And each normal mode, we remember to model as a harmonic oscillator. So it has the vibration of the medium is some kind of harmonic oscillation, and that involves momentum squared and position squared. So that means we get 1/2 kBt for the momentum showing up and 1/2 kBt for the position showing up. So that means that each normal mode gets kT for its energy associated with it. So if we distribute the energy equally to all of those normal modes, we should have that associated with each normal mode. And we now know how many normal modes there are in a frequency region. So if we take that number, multiply it times kb for each normal mode, and we can take the derivation we just had on the previous page, then this is the energy density as a function of temperature and frequency. So that's it. That's what they wanted to derive. They wanted to derive the energy density, the energy per unit volume as a function of frequency and temperature, and they did that here. Now, actually, they got the energy density, but the spectral radiance is simply related to the energy density by this C naught over 4 pi. So these are just constants. So this works out from this derivation to be given by this expression here. So that was Rayleigh-Jean's derivation, and it followed through exactly as we would do based on what we know about waves and the number of normal modes and what we know about equal partition theory, saying that each of these oscillations is going to get a kBt, so 1/2 from momentum, 1/2 from position gives us 1 kBt for each one of those normal modes, and that's the expression you get. So let's plot this versus the observed black body radiation curve and see how they compare. And this is what you find. This is, say, temperature 1500. This is the experimental shape, and this is Rayleigh-Jean's shape. And this was an epic failure, right? So it actually does an okay job. It has the right form here at very low frequencies, but very quickly, as you increase the frequency, it deviates away from the correct answer. So this was something that was called the ultraviolet catastrophe, because it predicted that at room temperature, objects should be emitting ultraviolet light or even higher frequencies. And of course, that wasn't true, because we knew that it had to go back down as you went to higher frequencies. So it emitted massive amounts of light at these higher and higher frequencies, and that was wrong, completely wrong. So it was called the ultraviolet catastrophe because it predicted ultraviolet. If they didn't know about X-rays at the time, if they knew about X-rays, they would have called it the X-ray catastrophe, but it was called the ultraviolet catastrophe. But no one could find anything wrong with their derivation. There was nothing wrong. They used the wave theory correctly. They used equipartition of energy theorem. At least they thought correctly. And just like we thought we did it correctly for heat capacities, there was nothing wrong. They couldn't figure out why the higher frequency modes, the higher frequency standing waves, were not filling the cavity. Okay. So that was just around the end of the 1800s. So we're getting around the time of around 1900 or so. So Max Planck started thinking about this problem in 1894. And again, I think he was getting funded by light bulb industry people. And he thought, maybe there's something wrong with the equipartition of energy theorem. We know that heat capacities is having a problem. Maybe there's something wrong with the way they're using the equipartition of energy theorem. And he knew that at low frequencies, it was working well, but it was only at high frequencies that it just catastrophically failed. So somehow there was no normal modes present at the higher and higher frequencies. So he needed some kind of behavior where the equipartition of energy theorem would behave like this. In the low frequency region, it would behave the way we expected it to behave from the derivations, that you would have KBT. But somehow, as the frequency went up, this had to go into this, where we had no contribution at the higher frequencies. So he wanted to try to make this happen. And the key step was this. He said he could achieve these limits if he assumed that each electromagnetic oscillation could only have discrete energy values of n, where n is an integer, that's the discrete values, and times the frequency with a proportionality constant that is given by this value. Now, we now call this proportionality constant Planck's constant, but he proposed this constant and said that this was the discrete, this determined the size of the discrete energy that you could have in the oscillations. And you can only have 0, 1, 2 sort of discrete quantized versions of this energy going into each oscillation. So at very low frequencies, this wasn't a problem, but at high frequencies, you see that to put the energy in at high frequencies meant you needed a lot more energy than at low frequencies, because the energy was now proportional to the frequency, which is strange because, remember, in waves, the energy is proportional to the amplitude of the wave, not the frequency of the wave. So for him to propose this was not something that anyone who understood wave motion would have suspected was needed. Okay? So that was a very strange thing to suggest. But what he did was he used this idea here, and he went back to Boltzmann's statistical mechanics, and we don't cover it in this class, but if you did cover this, you would see how you got the equipartition of energy theorem. He followed a very similar path, and he was able to derive, instead of the equipartition of energy theorem the way we learned it, he found that with these discrete energy packets, that the mean energy would have to take on this form as a function of frequency and temperature. And this has that limiting behavior that he was looking for. So in other words, if you take this part of the expression here, in the low frequency limit, if you do a Taylor series expansion of this exponential, it looks like this, and we can, low frequency, just stop it after the first couple terms. If you plug that into this expression here, then you see that we end up with 1 plus h nu over kBt minus 1. So we end up with just h nu over kBt, h nu over kBt, which just comes out to kBt. And that has the right limit. And then in the high frequency limit, this guy right here is just e to the h nu, and nu is infinity in the high frequency limit. So that makes this whole term go to infinity. You put infinity in here, and of course, that's just going to go to 0. So that was his transition from the correct value at low frequencies, which is some high energy, down to the correct value at high frequency. So the mean energy is going to be dropping. So then he goes back to Rayleigh Jeans and says, okay, everything that we did in counting the number of normal modes, that part is correct. Where they went wrong was in using just KBT as independent of frequency from what they expected from wave theory, and now plugging in his result, replacing their KBT with his result that has the right limits as a function of frequency, he gets this expression here. And then with using, again, the Rayleigh-Jeans derivation, which we know, for the number of normal modes, then we get this expression here. And this is Planck's black body distribution law. This tells us the energy. And that actually perfectly matches the experimental result. And he published this in 1900 and said, the only way I can get this to work is to propose this odd behavior here, which when you put it into Boltzmann's stat mech, gives you this value for the energy, and it leads to this expression, which agrees perfectly with all of the experimental results on black body radiation. So that strange leap he had to make was the beginning of the quantum revolution of quantum physics. And so that was just the beginning of it. So there was a lot more that needed to be worked out, but that was the step that needed to be taken in order to get people to stop thinking about energy as being associated with wave amplitude, but now being associated with wave frequency in this case. So that's it for this video. And the next video, we're going to be looking at more experimental evidence in the photoelectric effect.